Okay, so if you were not here yesterday, so what we did was move on from the lower bound and trying to understand the properties of this lower bound for best arm, and try to understand from these properties if we can come up with some ideas for an algorithm. So here we have a small recap. We are studying multi-arm bandit problems now. Bandit problems have k actions. Each arm is associated with a reward distribution, p theta a. A is the action, theta is the parameter of the problem. We make the simplification that for this distribution is simply a Gaussian of mean theta a and the fixed standard deviation sigma squared. Variance sigma squared. So that here this expected value of the reward when sampled from this distribution is exactly theta a. And our goal is to identify the best arm. So the arm with the largest mean value that we denote by a star theta. We're going to look at the fixed confidence problem. In the fixed confidence, we are trying to find a sampling rule, a stopping rule, and an inference. So our estimated optimal arm. This is basically a mapping from data to actions. And we are trying to minimize the sample complexity. So the average number of samples that we need, subject to constraints on the correctness. So in the following, there is a lot of notation here. I will not write pi, if possible. And the lower bound that we derive for best arm is simply that the infimum over all possible algorithms of the expected sample complexity is lower bounded by t star theta times the Bernoulli-KL divergence. Here you have the definition of the Bernoulli-KL divergence between delta and 1 minus delta. And as delta goes to 0, the first term is basically 0, and the second term becomes basically log 1 over delta. So this is the usual log 1 over delta term that you usually see. Then we have the characteristic time. The characteristic time basically quantifies the number of samples that you need on average. And you can think of the inverse as some sort of information ratio. And the inverse, it's the value of this optimization problem. So in this optimization problem, we are taking a supremum over W that belongs to the simplex of dimension K. W represents a distribution over arms, an infimum over alternative models of this expected log likelihood ratio. And here the alternative models are the models where the optimal arm is different from the optimal arm in the null model in theta. This will become handy today when we derive the delta correctness proof. And we have a number of properties. So if we denote by W star the solution, which is the best static sampling rule, we know that W star is unique. And also we know that the mapping from theta to W star theta is continuous. And this is also very important. This is important because in the algorithm that we derived, we are estimating the mean value of the rewards. So this is a changing value. And asymptotically, it will converge to the true value theta, and we're going to use this continuity to derive the sample complexity result today. And yesterday, what we did in the second half was to introduce track and stop with C tracking. The idea is based on the lower bound. So if W represents the best static sampling rule, so the best way we should sample the arms, then maybe we can just compute this W and then sample actions according to this W. There is a problem though. It depends on theta. We don't know the true value of theta, so we need to estimate theta, and if we don't estimate theta well, then our W star might be very different from the true W star. So the optimal allocation that we computed might be very different. So we need to do something different. We cannot simply compute the lower bound for our estimate of theta and then follow what the optimal solution tells us. So what we're going to do is called C-tracking. This is the rule. So the next action will be the one that maximizes this quantity here on the right. So this quantity here on the right, it's a sum over all the past rounds of this quantity here minus the number of times we pulled that action. This quantity, it's simply the projection of the optimal solution that we computed with at theta n. At theta n is our estimate of the model, is a maximum likelihood estimate. So we compute W star for this at theta n, and then we project it on the clipped simplex. The clipped simplex is defined here, is this delta epsilon n k, which is basically the set of all distribution such that the minimum probability over arms is epsilon n. So we are guaranteeing that each arm has at least probability epsilon n of being sampled. And we're going to take epsilon n as a decreasing sequence in square root t. So it's roughly 1 over square root t. And by doing so, we know by the Borel-Cantelli lemma that I showed you yesterday that we can guarantee that the number of times we sample each arm goes to infinity, almost surely. And because of the law of large number, then we also know that the maximum likelihood estimator will tend to theta, so the true value. And then by continuity of W star, we also know that W star at theta t will converge to the true W star theta. But this is all nice, but it's not really what we want. What we really want is that asymptotically, we can show that the average sampling of the arms converges to the true W star. So in the last part of the lecture yesterday, we showed this first result that says the number of times we selected this arm A minus this sum of probabilities of that arm. And here it's not WEN, but it's W star. So it's not the projected W star, it's W star itself. So this difference here is at most k times 1 plus square root t. So it's very important that it's square root t, because then when you divide by t, you know that the right-hand side will tend to 0. And so we use then this property to show that the average number of times we selected arm A will converge to this quantity using the Cesaro lemma. Okay, so this is where we stopped yesterday. If there is any question, super clear? Yeah. So what we're gonna do today is derive the stopping rule, and then from there we will derive the last result of the bandit chapter about the sample complexity. And so from tomorrow we will do MDPs. Okay, so we need to design the stopping rule, which basically tells you when to stop. But we want to design it in a way that it also guarantees the delta correctness, right? How can we guarantee the delta correctness? That's the main problem here. So as an idea, we can start by looking at the lower bound. So the lower bound always tells you a lot of information. So what does the lower bound tells us? The lower bound tells us that the number of samples we need is at least theta star theta times log 1 over delta. So why don't we just stop when t is bigger than this quantity? Well, this is a not so smart because we don't know theta, so we cannot really use this quantity here. And we are not really sampling according to the true W. So there are some differences. But this is a good starting point. The idea is that somehow we need to account for the fact that we are estimating the model and that we are converging to the true model. So this is a good starting point. We can maybe replace theta star theta with some empirical version. And the idea is we can define the empirical version of the characteristic time as the sum over the actions of NAT divided by T times the KL. Here, I forgot the infimum over alternative models. So here the infimum is over alternative models that are alternative with respect to hat theta t. Okay, because we don't know theta, so we are using our estimate of the model now. So we plug in our estimator here, and here the KL is between our estimate of the model and this alternative model here. So you can already see that because of continuity, asymptotically, this empirical characteristic time will converge to the true theta star. So we call this the empirical characteristic time. Okay, so we can replace this T star theta with the empirical version. This is the starting point. We need some additional factors, something that it's taking into account the fact that we are estimating the model, that this is not the true theta star. What we're going to do is try to use a technique called mixture martingale. This technique is quite cumbersome to use sometimes. We will try to use it today, go through all the steps. But I think it's a very general and useful technique. So I want to do this computation because maybe it will become useful for other problems. And I think it's very important for you to know. So to introduce the idea, yesterday I talked about martingales. I talked about submartingales, supermartingales. But what is a martingale? So to define the concept of martingale, first we need to know the definition of adapted process. So we are working this filtered probability space here. We have our sigma algebra. We have this filtration. And we say that a process xn is adapted if each xn is fn measurable. And we are going to write it in this way. Then a martingale Mn is an adapted process for each n. The absolute value of Mn is always bounded. And then the last and most important property is that when we take the conditional expectation with respect to Fn minus 1, we have the martingale at the last time step, Mn minus 1. And we also define a super martingale when the last property becomes an upper bound here. So on average, the expected value is decreasing. So why is this important? There are a couple of reasons. The first reason is that if you have a non-negative supermartingale, so if Mn is non-negative, then we know that any supermartingale, any non-negative supermartingale, always converges to a finite value, almost surely. And it's finite. What does this mean? It means that you cannot expect a supermartingale that is non-negative to like explode. You cannot expect spikes. So the main idea is, can we exploit this property to come up with a delta correctness rule, delta correct rule? The idea is that when you have spikes, is because maybe you are in this delta regime where maybe you have false positives. Okay, but this will happen with probability delta at most. So what we will do is try to come up with a martingale with a sequence Mn that is a super martingale under the null hypothesis. So under the null, you cannot expect spikes to happen too frequently, and if they happen, they will happen with a certain probability delta, and this will be the false positive rate. And we are going to use this tool called Wille's inequality. Sorry. So Wille's inequality tells us that if Mn is a super martingale under the null hypothesis, then the probability that there exists a time t such that mt is bigger than 1 over delta is upper bounded by delta. So this is exactly the statement I just said before in words. It's a sort of Markov inequality. So also Markov inequality, it's saying the same thing in a sense. Here we also have the expected value of m in 0. Okay, so you can already see that here, if we manage to come up with a good martingale, we can get this upper bound of delta, which is what we want in the end. The problem is, how do we connect this martingale to what I told you before about the empirical characteristic time and so on? So that will be the main computation today. But before we move on to this, I want first to show you that we can achieve this delta correctness if we have the right threshold. So let's go back. Let's go back here. And what I will show you now is that if there exists here, instead of log 1 over delta, we're going to use a different function that we call beta. Beta, that is a function of time and of delta. So we are going to show that. So here we have a proposition. So suppose that there exists a threshold function, beta t delta, such that the probability that there exists a time where t t it's bigger than the characteristic time, the empirical one, times beta t delta, it's smaller than delta, then track and stop is delta correct. So in this theorem, I'm assuming that this holds, okay? In the next, after we prove this, we are gonna show that this statement holds. So first I'm gonna show this easy result. And then after we are gonna move on with the martingale construction. But I hope, I hope this part, the main idea of the technique that we are gonna use it, I hope it's clear. Okay, so the starting point is to consider the event where we have not estimated well the model, so we don't know what is the, so our estimate of the best arm is not the true one. Our estimate of the true model, of the optimal arm is based on our estimate of the model. So you can think of this event as being included in the event where the true model is an alternative model for your estimated model. Right? Okay, so we start from this statement. So probability that tau smaller than delta E. So what is this statement exactly? So we are using a stopping rule, this one. So the minimum time t such that this inequality holds. So if tau is smaller than infinity, it's happening at some point, we can rewrite it in this way, the probability that there exists some time t, where t is bigger than the empirical characteristic time times beta t delta intersection with the event E. So what is this? This is also equal to the probability that there exists a time t. I'm gonna here multiply both sides by 1 over the capital T, so the empirical time, so that here we have t divided by t bigger than beta t delta. So what is the definition of the empirical characteristic time? It's this one. Here it's inverse. This is so the inverse, it's this quantity. When you multiply by t, this t will cancel out with the other t. So this t here will cancel out with the t that appears in the denominator. So we have infimum over lambda that belongs to the set of alternative models of theta at t, sum over a of n at, KL of theta hat at lambda a bigger than the threshold. And then we also have our event. But our event is telling us that at this stopping time, we have not estimated the true arm, which means that the true model is an alternative model for our estimated model. But if the true model belongs to the set of alternatives, then we can just plug in theta here. It's going to be an upper bound of the left-hand side. So the probability of this event occurring will be larger. So here I'm going to replace the lambda with the true theta. Bigger than the threshold. We don't need the event anymore because we used it. But by assumption, we know that our threshold satisfies this. So if we manage to find a threshold that satisfies this inequality here, so this probability is upper bounded by delta, we are done. We have showed the delta correctness. So let me repeat. We are going to use the martingale to find what is this threshold beta. But now let's suppose that we have found it. Suppose that it satisfies the Wills inequality, so that there exists a t such that t bigger than the empirical characteristic time times the threshold is smaller than delta. So if we manage to find this, then we can show that the track and stop is delta correct. So to show that it's delta correct, we need to look at when a false positive event happens. We define the false positive event, E. The case where our estimate of the best arm is not the true optimal arm. Since our estimate is based on the estimated model, it will be an argmax of our estimated model. Then it means that the true model belongs to the alternative set of models for our estimated model. Okay, so, and we are going to use this later in the proof. So the starting point of the proof is here. We start with this probability. We rewrite the condition that this condition here, tau less than infinity, as the probability that there exists a time such that the stopping rule triggers. We simply rewrite this inequality. We make the infimum over the alternative models appear. We know that theta belongs to the set of alternative models because we are taking an intersection with this event. And then theta might not be the infimum, might not be the point that minimizes the left-hand side. So it's an upper bound. And because it's an upper bound, this probability will happen with higher probability. So here we get this inequality, but then we know that this probability it's upper bounded by delta by assumption. Okay. Yeah, I hope it's clear. Okay, so perfect. Now we will try to do the derivation of what is beta. So we are going to show that if we take the threshold rule to be 2 log 1 over delta plus k log 1 plus t over k, then this threshold rule satisfies the Wills inequality. So the starting point is this mixture martingale technique. So let me first define what will be our martingale. So we are going to consider the likelihood ratio between two models. Here I'm going to use lambda as the parameter of this other model, but it's not an alternative model, okay? It's just a parameter. So the likelihood ratio of the data we have observed so far from round 1 up to t. And here, the numerator, we have the density of the observation in round n. And we consider this density with respect to the parameter lambda. And here we need to consider the parameter for the action an. And at the denominator, we will choose instead the density, but with respect to the null model, the true model. So why are we choosing this quantity? Why this will be a martingale? Why are we considering this? Just from an intuitive perspective, if the data is generated by theta and not by lambda, the denominator will have higher likelihood compared to the numerator. Okay? So what will happen is that on average, this quantity will decrease. You cannot expect this quantity to have spikes if the data is not generated by lambda. If you have spikes, they must occur with small probability. Okay. This is the starting point. The next step is to not consider just one single lambda. The idea is to take an integral over possible values of lambda. So this is inspired by betting, even though I don't like this analogy so much. But the idea is that all these possible different values of lambda are possible betting strategies. And when you consider all possible betting strategies, the probability that one betting strategy will work if the null is false, then it will happen. The idea is if theta is not the true model and lambda is also not the true model, then probably you're not going to see this spike. But then if you average over all possible alternative models and theta is not the true model, then one of these lambda will work. So here, when you choose lambda, if you don't average, if you just consider one single lambda, how do you choose the lambda? That's the problem. If the data is not generated by theta, you want to choose the lambda that maybe generated the data. But you don't know what is the lambda. So what you're going to do is take simply an integral over some prior distribution over lambdas. And if you choose the prior distribution in a good way, like a Gaussian or some distribution that gives probability mass to all the possible values of lambda, then if there is a lambda in this set that generated the data, you will see the spike. And so this martingale will not decrease. So the mixture that we will consider, it's MT, which is an integral over values of lambda. And here we denote the prior by pi. And we are going to use as prior distribution Gaussian of parameter theta with variance sigma squared. But first we need to show that LT is a martingale. And to show that it's a martingale, we can simply look at the expected value of a single observation sampled from some action under the null hypothesis. So what is this? This is simply an integral of this ratio, but it's an integral because here we have an expectation, and here the density of theta a will appear. So this density cancels out with this one, and then you are left with an integral of a density which is equal to 1. So when we can use this property now to so LT, it's a product, right? It's a product of these ratios. So this is also equal to LT minus 1 expected value of the ratio at the last time step. Which is simply equal to 1, and so we are left with LT minus 1. So I was able to bring out LT minus 1 because LT minus 1, it's measurable with respect to FT minus 1. So it's known. We don't have any randomness. And the only randomness that we have on average will be equal to 1. So all of this is equal to LT minus 1. So it's a martingale. We also know that it's positive because it's a ratio of densities. The densities are non-negative. So we are in the regime that we want. And when we take an integral here, also MT remains a martingale. So when you apply a linear operator, it still remains a martingale. So what we will do now is try to relate MT to our empirical characteristic time. So I'm going to define ST to be the sum over A of NAT, KL hat theta AT, theta A. So the idea is that if we manage to show, so what we have is that MT, it's a martingale, so it's also a super martingale. The idea is to apply Wilson inequality. So we know that delta is bigger than also this quantity here. So we apply the logarithm because it's a monotonic transformation. And then what we will do is try to show that log MT, it's lower bounded by ST plus some other stuff. And this other stuff will be the beta, the threshold rule, the beta T delta. So what we will do now is compute the integral and then try to find the lower bound. If we find a lower bound, then the probability of this quantity being bigger than log 1 over delta will be a lower bound of this probability. So ultimately, we have the delta is still an upper bound. Okay. I'm going to start by writing first what is the logarithm of LT. So with that, we can simplify it. So this is the log of the product from 1 to t of the ratio of the densities. And we know that each f it's a Gaussian, okay? So it's, I don't have much space here, but here it's x minus lambda squared divided by 2 sigma squared, all divided by square root of 2 pi sigma squared. So the logarithm, here the 2p sigma squared will cancel out in the ratio, right? So what we have left is minus xn minus lambda an squared divided by 2 sigma squared plus xn minus theta an squared divided by 2 sigma squared. This is also equal to minus 1 over 2 sigma squared. Sum over actions, sum from 1 to t of the indicator function that we have selected arm A around n times xn minus lambda a squared minus xn minus theta a squared. So here I'm just, we just need to simplify the expression. What we want is to make the empirical estimate of theta appear so that it's explicit, because our goal in the end is to find a lower bound on M that depends on ST, and ST depends on the empirical estimate of the model. So simply write explicitly the square. So here we have xn squared, but it will cancel out with this other xn squared. We have lambda a squared minus theta a squared minus 2 lambda a xn plus 2 theta a xn. So now notice that when you sum over n, this is simply the number of times you selected arm A. So this becomes NAT for these two terms. So we have NAT that multiplies lambda a squared minus theta a squared. And what about the other two terms? So this is a constant in time. This is also a constant. We just have sum over n of xn. But we know that theta hat at, it's 1 over n at sum from n equal 1 to t of the indicator function of na equal to a times xn. So this sum of the indicator times xn is equal to hat theta t times nat. So here we have this additional term, nat, that multiplies theta hat a t. We also have a factor 2, and here we have the difference between theta a and lambda a. The only thing left for this computation is just to make the square explicit. So we are gonna sum and subtract hat theta a t squared. So we have lambda a squared minus 2 theta hat a t times lambda a plus theta hat a t squared minus theta a squared plus 2 theta hat a t theta a plus theta hat a t squared. So I added and subtracted these two terms. Here there is a minus, I guess. So this simply becomes minus 1 over 2 sigma squared, sum over A, and A t that multiplies lambda A minus hat theta AT squared minus theta A minus theta hat AT squared. So now we made explicit the dependency on the empirical estimate of the model, which is what we wanted. Okay, this was the logarithm of the likelihood ratio. But remember that the MT, the mixture Martinger, the integral of the LT, there is no logarithm. So MT is also equal to the product over actions of IA, where we define IA to be the integral for a single arm. So this sum over actions becomes a product. So we have this exponential of minus 1 over 2 sigma squared times an AT that multiplies these two terms. I'm not going to write T anymore. Also, I will not write A in the following, just for simplicity. Yeah. So what's interesting here is that we can move out this quantity because it doesn't depend on lambda. So we are left only with computing the integral with respect to this term. So this is also equal to exponential of an A divided by 2 sigma squared theta minus theta hat integral exponential of minus n divided by 2 sigma squared times lambda minus theta hat squared. And this prior here, it's a Gaussian. So it's going to be exponential of minus what we said that it was theta, right? So here we have lambda minus theta divided by 2 sigma squared. And here we have square root 2 pi sigma squared and in the lambda. Okay, so just a small recap. Remember, our martingale was an integral of likelihood ratios. We showed that the logarithm of the likelihood ratios is equal to this sum over actions of this quantity. So we can factorize the integral as the product of this IA, where IA is a single integral. And this IA, it's just the integral of this exponential, and the exponential, here we have this quantity that we derived before. We are taking an integral with respect to a Gaussian prior, and the Gaussian here, it's of parameter theta and variance sigma squared. So we can simply rewrite the integral, writing explicitly with the density, and this is the density of this prior. Yeah. So the next step is computing this monster here and try to simplify it and understand what we can do. So What's really important for us is understanding what is this quantity here. Because when you do the product of these two exponential, it will become a sum of the terms inside the exponential, and the term that you have inside the exponential, it's basically this quantity divided by 2 sigma squared. So we need to simplify this quantity here. So we just need to write it down and make explicit what are these two quantities, and try to simplify in lambda, because the integral is with respect to lambda. So here we have n lambda squared plus n hat theta minus 2n hat theta plus lambda squared plus theta squared minus 2 theta lambda. So we cannot simplify the lambdas because we have dn. So we get 1 plus n lambda squared. Then we have the cross product. Plus n hat theta plus theta squared.
Theta hat square in the first one, the second term of the hat of the.
This one? This one, right? Or no, sorry, this one. Yeah, yeah, thanks. And I also forgot the lambda here, I think. Yeah. So yes, so there is a lambda appearing here. Okay, so with the lambda, okay, so now we have this lambda squared, then we have the 2 lambda here. We need to complete the square with the lambda. What we can do maybe is we can divide and multiply by 1 over n here. So we divide and multiply by 1 over n, so that then we can write lambda squared minus this quantity. Oh, sorry, thanks. So here you can write 1 plus n lambda squared minus 2 lambda m, where we define m to be this ratio, and hat theta plus theta divided by 1 plus n. Plus n hat theta squared plus theta squared. So to complete the square, we can just do plus minus 1 plus n m squared. So this becomes 1 plus n lambda squared minus 2 lambda m plus m squared plus n hat theta squared plus theta squared. And here we have a minus 1 plus n m squared. So this becomes lambda minus m squared. Okay, this is what we wanted, because now we have lambda just here. It's a simple square. We don't have lambda appearing anywhere else. So we just we could move this out of the integral now. Before we do so, we can still simplify this quantity. So we are going to look at this quantity now on the right. So what is m? M is written here. So we can write here the numerator. We are taking the product between 1 plus n and these two terms. So we have n at theta squared plus theta squared plus n squared at theta squared plus n theta squared minus 1 plus n. And here we have n at theta plus theta squared. Sorry, we don't have this term anymore because it's simplified. Because we have 1 plus n here, this is m squared, and it simplifies with this quantity. And here it's a minus. Okay. So we can see that there will be some simplifications. I will write the full expression. N squared at theta squared plus n theta squared minus n squared at theta squared minus theta squared minus 2 hat theta and theta divided by 1 plus n. So we simplify these two quantities. We simplify also this one. So we are left with n that multiplies at theta squared plus theta squared minus 2 at theta divided by 1 plus n. And so this is simply n divided by 1 plus n theta hat minus theta squared. Like black magic. Okay, so where are we? Here, this becomes n divided by 1 plus n times theta hat minus theta squared. This other quantity becomes 1 plus n times lambda minus m squared, right? So our integral IA is also equal to exponential of. So now let's go back and look at the expression of IA. So IA, it's this stuff here. So we have this quantity. And we also have the additional contribution from this term here that comes from inside the integral. Because remember, we simplified the sum of this expression. And since there is a minus, here we get minus n divided by 1 plus n theta hat minus theta squared. And what will be inside the integral? It will be exponential of minus, what did we have here? We had 1 plus n lambda minus m squared divided by 2 sigma squared times 1 over square root 2 sigma squared. So we are almost done because this is like the density of a Gaussian. We just need to fix the variance term. So we can multiply and divide by square root of 1 plus n. So this integral becomes integral of exponential minus 1 plus n lambda minus m divided by 2 sigma squared. And here we make the 1 plus n appear. The lambda that multiplies 1 over square root of 1 plus n. So this is the integral of the density of this Gaussian here. And it will be equal to 1. So since this integral will be equal to 1, then all of this is just equal to 1 over square root of 1 plus n. So in the end, our integral term is exponential of this quantity times 1 over square root of 1 plus n. We need to simplify this quantity here. We also have the 2 sigma squared. So it will become n squared theta minus theta hat divided by 2 sigma squared that multiplies 1 over square root of 1 plus n. Yeah. So I didn't write all the subscript because otherwise it will be too cumbersome. But these are all theta a, theta hat at, and at. Yeah, I think we didn't lose anything during the process. So MT, it's the product of these quantities. Oh yes, we lost the 1 plus n here. Are you still with me? Yeah. Yeah, it is a lot of computations, but I think it's good to do it at least one time. So going back to the original idea was we need to take the logarithm and find the lower bound on MT. So let's take the logarithm. So logarithm of MT will be equal to minus, so we have a sum over actions of minus 1 over 2 log 1 plus n at. So this corresponds to this term plus n at squared times theta a minus theta hat at squared divided by 2 sigma squared 1 plus n at. So we are gonna find an upper bound on this term because we have the minus. So with the minus term, it will become then a lower bound. So we are gonna exploit the fact that the logarithm is concave. So we can use Jensen inequality. So we have a sum of this logarithm. We can divide and multiply by k. So this is like k expectation over a uniform distribution of log 1 plus n at. And by Jensen inequality, since log is concave, this is smaller than k log of the expectation of 1 plus n at. which is simply 1 over k sum over a of 1 plus NAT. And this becomes k log 1 plus t divided by k. So this is the second term that appears in the threshold rule. So this is an upper bound. So with the minus sign, it will become a lower bound of this quantity. Regarding this other term, if we manage to get rid of Na divided by 1 plus Nat, then we are left with sum over A of our KL divergence, basically. So what we are going to show now is that n squared divided 1 plus n is bigger than n over 2. So for n equal to 0, this holds. Now for n bigger than 0, this is simply this inequality, which always holds for n bigger than 1. So we have just shown that this inequality holds for all n including 0. So we are going to simplify this na squared divided by 1 plus na. We are going to lower bound it with na divided by 2. So log mt, it's lower bounded by minus k log 1 plus t divided by k plus sum over a of nat divided by 2 sigma squared times theta hat at minus theta a squared. This is just minus k log 1 plus t divided by k plus 1 over 2 sum over a of nat kl between theta hat at theta a. And so we have basically reached the conclusion that we wanted. So by Wilson inequality, we know that delta is bigger than this probability. We apply the logarithm because it's a monotonic transformation. But then we just found this lower bound on log mt. So this, we call it st, the original quantity that we wanted. So we have that 1 over 2 st. Here we also have a factor 2. It's bigger than log 1 over delta plus k over 2 log 1 plus tk. So you just multiply by 2 and we have proven the result that we wanted. This is k. Yeah, so I think we can take a break. Yeah, let's take a 10 minutes break, and then we're gonna just prove one last result, which will end the bandit chapter. Okay, I hope you can hear me online. So during the break, I was answering a question about the fact that at the very end here we get this threshold rule, but this threshold rule is not the best possible threshold rule we can compute. It will not be optimal up to a multiplicative factor 2, and this is the factor 2 that makes the threshold rule not optimal. in the computation, I chose a prior that makes the computation very easy. It's a prior that it's a Gaussian centered in theta with variance sigma squared. Which means that if the true model that generates the data is very far from theta, so let's say the true model that generates the data is here. Let's call it theta prime. And let's say it's very far. Since we have put the Gaussian on theta, the Gaussian will tend to zero very quickly. So if this theta prime belongs to the tail of the Gaussian, and the probability of this theta prime is very small, so the likelihood of this theta prime is small, then you are discounting this model too much. And this is also a reason why we get this suboptimality factor 2. In reality, it should be 1. How can we deal with this problem? We just choose a different prior, but then we need to go redo all the computations, and they will not as nice as I showed you today, even though it didn't look nice. So the idea is maybe to choose a prior that is like, you can still choose a normal distribution centered in theta, but you make the variance different. You choose a parameter rho. This is a fictitious parameter that you introduce. And then you also introduce a prior over rho. So not only you have a prior for the value of lambda, but you also introduce a prior for rho, and this can be some heavy tail distribution. So in the end, we are going to do two integrals, 1 over lambda with this prior, and 1 over rho with some heavy tail distribution. And I didn't do the computation, but I think you can show that this 2 becomes 1. But I mean, it's a long computation just for like this constant factor. I don't think it's worth it, but that's the idea. And I hope you get the intuition of why we should do this. Because we want our martingale to explode in case the true model is not theta. But if the true model is theta prime, it will take longer for the martingale to explode. Yeah. So we have derived our threshold rule. And so the stopping rule, it's simply the infimum over time steps such that t is bigger than our empirical characteristic times the threshold. And the threshold, it's the one that we just derived, k log 1 plus t over k plus log 1 over delta. So now we are going to show what is the upper bound for the algorithm. So theorem. So track and stop satisfies probability under theta, limit as delta goes to 0 of tau divided by log 1 over delta. It's upper bounded by 2 t star theta. This is with probability 1. So what this means is that asymptotically, we are optimal up to a constant factor 2. Because if you remember, the lower bound was saying that the expected sample complexity, it's lower bounded by t star log 1 over delta. You divide both sides by log 1 over delta. And so when you take the limit, this also holds. So the lower boundary t star, and here we have found an upper bound that is 2 times t star theta. So asymptotically, we are optimal up to a constant factor 2. And this two factor is the two factor I discussed before that comes from here. Okay, so proof. And after this, we are done and we can go. So the proof relies on the continuity of the characteristic time, the empirical characteristic time. So we know that tau is the infimum So we know that this quantity is continuous, and we also know that it will converge to theta star, t star theta. So it will converge because we know that theta at t converges to theta almost surely. And we also know that an a t divided by t converges to w star a theta almost surely. So remember that the empirical characteristic time, it's this quantity with the infimum. So because all these quantities converges to the, so we have at theta t that converges to theta, the average sampling converges to the optimal sampling by continuity, then we have that also the empirical characteristic time converges to t star theta. So by continuity, we know that for each epsilon, there exists some time epsilon such that 1 plus epsilon t star theta will be bigger than the empirical characteristic time. So we are sufficiently close, we are epsilon close, okay? So the idea is that we want to study this inequality in terms of t star. So we fix some epsilon bigger than 0. And by continuity, we know that there exists this time t epsilon. So at t epsilon, if we consider this inequality, so if we consider the time step that solves this inequality, then this time step is also a time step that satisfies this inequality. Right? So as soon as we reach t epsilon, basically we know that we have stopped. So what I want to do here is to show that tau is upper bounded by t epsilon and the infimum over time steps that satisfy this condition. So this inequality might be satisfied also before t epsilon. So to be sure, we take the maximum between these two, so that we know that at the epsilon also this other inequality will be satisfied. Okay. So we take the maximum between these two quantities. What will happen is that after when we divide by log 1 over delta, this will be t epsilon divided by log 1 over delta, but as delta goes to 0, this will converge to 0. And this will be the dominating term. So we need to look at what is the minimum value of t that satisfies this inequality. So we need to find the solution to this problem. And here we have 2 log 1 over delta plus k log 1 plus t divided by k. And the problem here is that t appears inside here, but it's also inside the logarithm. So let's give some names. I will call 1 plus epsilon t star to log 1 over delta. I will call it A. 1 plus epsilon t star times k, I will call it B, times log 1 plus t over k. Then I define x to be t divided by k, alpha to be a divided by k, and b beta, not to be confused with the previous beta, to be b divided by k. Now we just need to solve this inequality, so that's why I'm doing all these transformations. So it's a bit simpler. So we have x bigger than alpha plus beta log 1 plus x. So we are going to use that log 1 plus x is upper bounded by the square root of 2x. So in 0, it holds. You can show that this is true by looking at the derivative of this function. So when we take the derivative, this is, so we get 2 square root 2x, the 2 will simplify, minus 1 over 1 plus x. So is this bigger than or equal to 0? Yes, because you obtain this condition here, which is always true. So f prime is non-negative, so it's this inequality is valid. So any x that will satisfy this inequality here is also an x that satisfies this inequality, because this quantity is bigger than this quantity. Okay, so we are looking at this different inequality, which is a stronger inequality. So let's denote square root of x by y. So we have y squared minus beta square root of 2y minus alpha bigger than or equal to 0. So a solution is given by beta square root 2 plus square root 2 beta plus 4 alpha divided by 2. So this is simply beta divided by square root 2 plus square root of beta plus 2 alpha divided by square root 2. And x was equal to y squared. Plus the cross product here. But what was x? X was equal to t over k. So t is bigger than or equal to k, that multiplies all this stuff. But what's important here is the alpha term. Why? Because so a is equal to k alpha, and a was the term that includes this log 1 over delta. So it's the important term because then when we let delta go to 0, it will be the term that goes to infinity. So it will dominate everything else. So here we have alpha. Here we also have square root alpha. But since there is a square root, this is not the dominating term. So alpha will be the dominating term. Alpha is a divided by k plus small order stuff. So this a is equal to t star 1 plus epsilon 2 log 1 over delta pu low order terms. And so we have found a solution to our inequality here. So we know that we can now upper bound the tau. So we know then that tau, it's upper bounded by the max between t epsilon and 2 t star 1 plus epsilon log 1 over delta plus low order term. So when you divide now by log 1 over delta, when you let delta go to 0, log 1 over delta will tend to infinity. This will tend to 0. This will tend to 0. And so we have just found that in the limit, the sample complexity divided by log 1 over delta is upper bounded by 2t star theta 1 plus epsilon. And now we just let epsilon go to 0. Because by continuity, we can always choose any epsilon, so we just let epsilon go to 0. And so this tends to 2t star theta. So what this is saying is that asymptotically, as we make our false alarm rate delta smaller and smaller, the algorithm will approach optimality up to a constant factor 2. But it doesn't say anything about optimality for small values of for large values of delta. So like delta equals 0.2 is a pretty large value. We don't know anything about the optimality in that regime. So this only tells asymptotically as delta goes to 0, but doesn't tell us much more. So this is like an active area of research to try to understand what happens for moderate values of delta. There are some results for the unstructured case, but also for MDPs or for other kinds of models, it's not very known. Okay, so if there is no question, we can stop here. And we will continue tomorrow with different models. We will work with Markov decision processes. And we will try to do the same thing, trying to derive a lower bound and then from the lower bound derive an algorithm. We will not do the computation that we did today. We will not prove again the stopping rule. So we will try to be a bit quicker. The main problem with MDPs is that the lower bound will be non-convex. So when we computed the lower bound yesterday, we used the fact that the alternative set can be decomposed as union of convex sets of alternative models, but that will not be the case with MDPs. So with MDPs, those alternative sets are non-convex. So we have to come up with a different solutions to deal with this problem. Yeah, okay. So thank you for attending.